Yeah, the last time I gave a talk in the seminar was during COVID days, so on Zoom. So this is much better, though even though now I still have Zoom on. And this room is amazing. So let's see how it goes. Yeah, I will tell a story about a variant of mainly constraint satisfaction problems, but then towards the end I'll get to a variant called promise CSPs. And there's a very pleasing theory here which relates mathematical structure to tractability. So that's mainly the thing I hope to get across. And it's more like a survey style talk. If there are any questions, stop me. Okay, I'll start really warm up very gently. So we all know an easy task, which is to two-color a graph. So I give you a graph, two colors, red and blue. Can you color it so that there is no monochromatic edge? So of course, there is a very simple algorithm. Start with some node, color it, propagate the colors. And if you never reach a contradiction, you have a true coloring. If you reach a contradiction, you have found an odd cycle, which cannot be two-colored. End of story. So you have a linear time algorithm. All right, so it's an easy task, linear time in the size of the graph. Okay, if you cannot two-color a graph, you really need three colors. And then you ask, can you actually do it with three colors? Well, then, of course, for the odd cycle, you can do it. But in general, this is a hard problem. Once you color, the neighbors have two choices. They are not fixed, so the natural algorithms all face combinatorial explosion. In fact, the best known algorithms, you can beat the naive 2 to the n quite a bit, but the best algorithms are still around 1.32 to the n. Okay? And of course, we expect this because it's an NP-hard problem. Okay, and there are also hard forms of two coloring. So if instead of a graph, you think about a three uniform hypergraph, so which is basically vertices and triples as edges, and then ask, can you color it with red and blue so that there is no monochromatic triple? This is also one of the classic old NP-hard problems. Okay, and therefore we do, this also takes exponential time for the best known algorithms. So we see a big complexity dichotomy here. So problems like two coloring are easy, solvable in linear or polynomial time. Two coloring hypergraphs, on the other hand, requires exponential time. It's NP hard. And this is a big chasm in complexity. So got this dichotomous behavior. And so today's story is going to be about this dichotomy behavior for these natural class of problems. And perhaps more importantly, also an explanation of what governs it. Okay, so we not only want to say which is easy and which is hard, but we want to understand why is some problem easy, why is some problem hard, kind of like a science of algorithms, if you will. Okay, so that's the really grand goal could be, can we somehow explain complexity? What structure in a problem makes it easy? And we know some things like this, right? Like convexity usually makes continuous problems easy and so on. So we would like to understand such things for broader classes of problems, and somehow maybe the lack of such structure makes it intractable. Okay, and this would be nice. It would be a little bit like the theory of everything for algorithms, but maybe that is too much to hope for, because there's a huge scope of problems and algorithms can be devilishly clever. So maybe you shouldn't have expect a universal theory. But you can look at fragments of problems, and in particular, constraint satisfaction problems are this broad class for which we have a very good answer for this. And that's the story I would like to tell you today, and some of the attempts to go beyond that to expand the reach of such CSP-like theories. Okay, so the philosophy in explaining complexity through structure is that somehow the symmetries in the solution space can shed light on its tractability. Okay, and this is encapsulated by this concept of a polymorphism. It's an operation under which the space of solutions is closed. I'll define this formally shortly. But I want to start with a very familiar example of a problem we all know and love and know how to solve efficiently, which is solving a system of linear equations over fields or rings. Okay, so you have Ax equals b, and you want to know, is there a solution x which satisfies this system of linear equations? And of course, we know how to solve this with over fields Gaussian elimination and by other methods for integers and so on. But there is one interesting closure property here, is that if you have three solutions to this system, then you can take this affine combination x1 minus x2 plus x3. This makes sense in any ring because you have +1 and -1, and that is also going to be a solution. And in general, any affine combination. Sorry? Yes, oh good. So these xi's are three solutions. So ax1 equals b, ax2 equals b, ax3 equals b. So if I take any affine combination, that will also satisfy ax equals b. So that's a nice closure property, right? And you can capture this closure property by something called this polymorphism, which is the following thing. It just takes 3 elements from your domain, let's say rationals, and it computes f of ABC is a minus b plus c. Now we have this vector x of different entries. If you apply this arity 3 function to 3 solutions component wise, you get a new solution which satisfies this. So the key thing in this polymorphism is that you apply it for each variable independently, ignoring all the other variables, and yet you're able to produce new solutions from existing solutions. So it's some sort of a higher order symmetry in the solution space. Mm-hmm.
So would the polymorphism be based hardness apply even to sort of equations over the rationals, like infinitely?
No, so this is more like, see, of course, from this polymorphism to the algorithm, there is no direct translation. So this is maybe more a guiding principle, and you still have to go look for the algorithms. And I think that's somehow the point. Yeah. And we will see that too. So somehow this translation is not direct. But the lack of polymorphisms in this context I'm going to talk about leads to hardness relatively easily for CSPs. Okay. This is more to just kind of warm up to sort of see polymorphisms. I really want to talk about it in the context of discrete problems. For example, let's take 2 coloring. So here is a graph which is 2 colorable. I deliberately made it disconnected, so you have multiple 2 colorings, right? So I can take 3 2 colorings here, 1 and 0 being red and blue, let's say. And if I take 3 2 colorings like this, I can now do one thing. Now I can take the component-wise majority, and that will be another 2 coloring, but you can prove that it will be a valid 2 coloring. Okay, that's very easy to check just edge by edge. Okay, because the majority has to differ from the other edge because in each one of them they were opposite. So this closure property then is that if you take component-wise majority, I can manufacture a new 2 coloring. Okay, and we say that therefore this 3-bit majority function is a polymorphism. It can take 3 solutions and locally apply the majority, and you get a new solution. And of course, 2 coloring is also a system of linear equations over F2. So from what I said last slide, you have other polymorphisms. For example, the parity function in this case is also a polymorphism. But you have 2 different kinds of polymorphisms. And of course, we know many algorithms to solve this, and I'll show you some algorithms for this as just a template for this connection between polymorphisms and tract algorithms. All right, so 2 coloring graphs, very good. Polymorphisms are there. What about 2 coloring hypergraphs? Okay, let's take the simplest hypergraph. It's one edge. Let's take 3 2 colorings of this. And okay, majority was good for me, so let me try majority. Okay, it doesn't work, of course. And okay, that was maybe a bit silly, but you might say, okay, maybe there's a more clever operation on 17 colorings, which will give you something. And the answer is sort of no. There are really no interesting polymorphisms in this case. And this interesting, I simply mean you can always copy a coloring or you can flip a coloring, ignoring all the other ones. So these are these dictator or anti-dictator functions. Those are going to be polymorphisms. I'll come back to this again. But besides this, you can prove that there are no interesting polymorphisms. And this is a combinatorial fact. There's no complexity here. For this relation of not equal on 3 bits, there is no interesting polymorphism. No, you can just check any, you assume there is an arity m function and you will get you will prove it has to be a dictator. So there is no a priori bound as far as I know. But anyway, the proof doesn't need it somehow for this particular predicate. And indeed, you can do this for any NP-hard predicate. I mean, it can sometimes get a little bit tricky to show it for any individual case, but this case, I believe, is not too bad. And the same holds for graph 3 coloring also, and these are all NP-hard problems. Okay, so of course, it's too much to extrapolate from maybe just these 2 simple examples, but really, you can see the yes. The polymorphism has to be applied to each thing separately. I'll define this in a bit. Same rule. Same rule has to be applied to each of these things, and it has to preserve the relation. And the name polymorphism comes because you take multiple homomorphism basically maps from relation to relation. Here you take multiple copies from the relation and map it to the relation. It's a higher order symmetry of the relation. I'm not sure I understand. You have to apply the same. Yeah, that's a function. Yeah, that's allowed. Yeah, it doesn't have to be a symmetric. Yeah, exactly. So polymorphism does not have to be symmetric. It can do whatever it wants. It can be any Boolean. Yeah, And I'll define it formally in the next slide. So polymorphisms are local operations to combine multiple solutions to a new solution. And for this rich class of CSPs, which I'll define next, we have this precise link between mathematical structure and complexity. A CSP is, assuming P not equals NP, of course, a CSP is tractable if and only if it has interesting polymorphisms. Okay, that's really all there is to it to explain complexity. Okay, which is very pleasing for this class of problems. Okay, so I need to define some things formally, in particular CSPs and polymorphisms. That's what I'll do next. So CSPs, all of you probably have seen this. So you have some finite domain. You can also talk about infinite domains. I'll restrict to finite domains. And you have some fixed predicate. In general, you have a collection of predicates, some fixed collection of predicates, but let's think about one to illustrate the theory. And how does an instance of a CSP look? So the template, the CSP is really specified by this predicate P. So you can talk about it as CSP of P. And an instance of this is going to have some number of variables. That's the input size. And a collection of constraints, namely P, applied to certain tuples of variables. Okay, so that's how it looks. So here I've assumed arity is 2, so that's how it looks. And you can ask many things about this CSP, but here, since I've written a conjunctive formula, I'm going to ask, is this formula satisfiable? So is there an assignment of domain values to the variables, which makes all the clauses, all the predicates happy, namely this formula is true. And that's the decision version. You can also ask the search version, find me one if it exists. Okay, so those are the natural problems which we know and love. So NP complete, pre-sat is NP complete, etc. comes from. Okay, so that's what it looks like. And just as an example, if P is this predicate which checks two things are not equal, then this is simply checking if that graph is colorable with the D colors, because each constraint is an edge, and you're checking that the two endpoints must get different colors. Okay, so graph coloring can certainly be encoded this way. And in general, that's the same thing. As I said, you might have multiple predicates, so we call it gamma. And the only difference is that you're not limited to P. You can, for each tuple you pick, you can pick one of the PIs from gamma, assuming the arity matches, and then apply it. Okay? And the question is the same. There's a lot of subscripts there. You don't have to read them. So. And just to give some examples, I already talked about graph coloring as an example. Hypergraph coloring is also an example. Again, keep your domain to be Boolean, and the constraint is now arity 3 and checks that not all 3 of them are equal. Like 3-sat, there is this problem 1 in 3-sat, which I like a bit more because you don't need negations. It just has one predicate which checks that exactly one of them is true. Yes, the arities could be different, yes. In general, they're arbitrary predicates. Yeah. The AIs could be different, yeah. Yeah. And I have one more example here. You can encode graph connectivity this way, directed graph connectivity, but 3 predicates. You can have a constant 0, 1, and then x implies y. Okay, so you're allowed multiple predicates of different arities. Okay, and graph K coloring, the same thing as 2 coloring, just change the domain. And unique games, you all might have heard of. That's also a CSP where the domain can be large, and the relations, you can predicates relations, same thing. The relations are basically bijective functions. That's what unique games is. Okay, and so these are all CSPs, and many, many more examples, of course. And yeah, so now with this theory, we have an explanation of when all of these things are satisfiable, tractable via polymorphisms. So finally, what is a polymorphism? You define a polymorphism for, let's define it for a single relation or predicate, P, a function of arbitrary arity from the domain D to the M to D is a polymorphism for P if whenever you take M tuples in P, arbitrary M tuples in P, you apply F component-wise, you will get another K tuple, right? There are M K tuples, each one of them in P. You apply F component-wise on the columns, you get a new K tuple that must also be in P. So no matter which M tuples I take, applying F will produce a new tuple in the relation or in the predicate. Okay, hence the name polymorphism, right? So it's like a homomorphism will be just a map from D to D, which preserves the relation. Here, it's polymorphism because it takes multiple domains. Okay. All right, so that's the thing. Now, why should this exist? And the set of all such things is called pol of P. And this, at least some non-trivial ones exist because you can have these functions which just copy one of the rows there. So these dictator functions, and those are always polymorphisms. Okay, so those are boring because they're not combining solutions, they're just copying solutions. So those are sort of the boring polymorphisms. And in general, if you have multiple predicates, you can just take the intersection of the pol of P for all predicates. Each should preserve every relation in your template. Okay, that's the way you define. Okay, so this is the same definition from last time. You can think of it as a matrix. You line up rows from P, apply F column wise, you should get a new row in P. That's what a polymorphism is. And just to ease in with some examples, I already told you two coloring. So if each of the rows is unequal, you apply majority 3. If you take a 3 by 2 matrix and do this, you will get a new row which is unequal. And note that for a general instance, if you preserve every relation, the general instance is just a conjunction of all these relations. So you will also preserve satisfiability for the full instance. So it really becomes a finite problem of understanding polymorphisms of this a particular relation or predicate. Okay. Input size, etc., is not relevant. Okay. And that's also the nice thing. You're explaining something infinite with something finite. So let's take this other predicate, XOR. So you want to check the predicate is just x plus y plus z mod 2. Checking it as an odd number of ones. So this also has polymorphisms. You probably guess what it is. Let's take, just for kicks, 5 satisfying assignments. Each row has an odd number of ones. How can you combine it so that the new row will have an odd number of ones? Okay, just take XOR, right? So if you take column-wise XOR, you will get something which will also have an odd number of ones. Okay, and that's easy to see because the entire matrix has an odd number of ones. So this must also have an odd number. So that's a non-trivial polymorphism. And now if you go to 1 in 3 SAT, you can try as much as you want. You can line up, you can take an M cross 3 matrix for any M you want, but you will always, the only thing you can do is dictate. Okay, so that doesn't have any problems. So a big goal in this CSP thing, really pioneered by this Federer-Body dichotomy conjecture, was for any CSP, the problem is going to have this dichotomous behavior. Either it's going to be polytime solvable or it's going to be NP complete. Okay? And yeah, of course, empirically, we see this with all the examples. 2 SAT is NP, 3 SAT is NP complete, all sorts of things. But this conjecture said that this always happens for every domain. And in fact, this was already known for the Boolean domain, which is perhaps the most familiar to us from the 78. Right? So if you take a Boolean domain CSP, there are essentially 6 cases which are easy. Like this, I mentioned this 2 SAT, you might know Horn SAT, and of course linear equations, and a couple of trivial cases where setting everything to 0 or 1 makes the problem satisfiable. These are the only easy cases, and the rest are all NP complete, as shown by Schaefer in 78. Okay, that's all good, but the Federer-Body conjecture was about any domain. And where do polymorphisms fit inside this? In fact, there was a refinement of the Federer-Body conjecture, which is then became called the algebraic dichotomy conjecture, which actually said that, well, not only is there a dichotomy, we can explain the dichotomy. Namely, the problem will be polytime solvable exactly when the relations admit a non-trivial polymorphism. Otherwise, it's NP complete. Okay, that's the more refined form of the conjecture, which of course implies the Federer-Body conjecture, but gives you more information. And namely that tractability is governed by these polymorphisms. And of course you want to test this theory, backward compatibility, right? And it of course holds for the Boolean case because all these tractable cases have some simple polymorphisms. So 2 SAT I've already mentioned, 2 of them I already mentioned. 2 SAT and linear equations have majority and parity. I showed parity 5, but really parity, any odd parity works. 2 SAT, any odd majority works, and so on. And the other cases also, for example, Horn SAT has just 2 variable and. That's a polymorphism. So these all have polymorphisms, some simple polymorphisms, and they're solvable. Any other case lacks polymorphisms, and they're not so. Okay, so that was for the Boolean case. And then there was a sequence of works over first ternary, quaternary, and things like that, and some other special cases, all culminated in couple of independent works about 7 years ago by Andrei Bulatov and Dima Zook, who actually settled the conjecture in the full generality. So they proved the algebraic dichotomy now theorem. Namely, polymorphisms lead to algorithms. Lack of polymorphisms makes you intractable. Okay. Yep, Peter. Uh-huh. Yeah, you can. Yeah, very good question. You can actually always produce that by taking small ones and composing them. So you can always get, once you have majority 3, you will also have majority 5, majority 7, and so on. One way there is no small thing. A priori, you would think there should be, right? But there are these deep theorems in universal algebra which says that you will always have a polymorphism of arity 4. So it somehow, I mean, I don't know how to prove that, but that's true. And in particular, that's related to this question of, is this criteria decidable? And in fact, it's very much decidable, because all you have to check is that, is there some polymorphism of arity 4?
Does this theory extend to infinite domain? For example, if I wanted to consider correlation constraint, would it apply?
Yeah, there is a theory of this, but I think it's believed that you have to be careful to pose these questions in the algorithmic sense. I think in general, it's not. I think it's not believed that there's a dichotomy, but there's a rich body of work which I'm not that familiar with. Yeah, but yeah, correlation clustering I've not thought in this context. Good point. Yeah, but here I'll only focus on finding. Yeah, but also your question, Peter, is a good one, because you will see in promised CSPs, one of the difficulties is that we can't really work with these small polymorphisms. Inherently, we'll have to deal with longer ones. Yes, I'll come to, yeah, the end of my talk if I don't run out of time. Sorry? Yes. Yeah, so actually Avi just stole my next 3 slides, so let's see that. So that's what I'm going to say. So this theorem has 2 directions, right? Hardness and easiness. Okay, so let's see the hardness first. Okay, and that one is somewhat easy. So how does one show hardness? Our power tool is reductions, of course. Namely, if A reduces to B, let's say by a polytime reduction, then if A is hard, then B is hard. This is how we build our NP hardness things. So to prove something is NP hard, we just have to reduce some NP hard problem to that. And so that's how we do the business. For example, my favorite problem is 2-coloring hypergraph. So if I reduce it to some problem, that problem is hard. And let's just see a little example, not necessarily the details, but how will you show, for example, 3-coloring is NP hard if you know 2-coloring hypergraphs is NP hard? Well, you will make a little gadget, right? So you know not all equal of 3 things is hard. So you'll take this x, y, z, and you'll try to build a little graph, right, on some vertices, such that if that graph is 3-colorable, then x, y, z must get different colors, right? So the usual things we do. And it turns out this graph actually works, and you can prove it by a couple of case analysis. If the outer things don't have all the same color, you can color the inner triangle. If they all have, for example, illustrated here, but if they all have red, you're in trouble, because one of the 3 inner triangles must get red, and you can't color it. Okay, so that finishes the proof, and and of course, when we teach this in classes, people are always like, okay, how do you come up with these reductions? What's going on, and so on. But somehow the story we don't necessarily always tell them is that there's a science to this, this sort of reduction game. Namely, such local gadget reductions are completely characterized by polymorphisms. Okay, and this is a theorem, and this is no computational aspect, it's a combinatorial theorem. A gadget reduction suitably formalized exists from one CSP to the other if and only if P has more polymorphisms in a formal sense than Q. Okay. And so one direction of this is pretty easy. If you have a reduction, you must have more polymorphisms because you're easy. The other direction is also not difficult. It has some flavors of long code testing and dictatorship test, which we kind of do in approximation, but was also done in this community. So essentially, one mantra you can have is the richer the polymorphisms, easier the problem via these reductions, right? And okay, so more you can, yeah, it basically there's a concept of like a map between polymorphism things, just because they could be on different domains, so it won't be containment, but pretend it's containment. Yeah. Yeah, so one direction is easy because, yeah, essentially, if you preserve it here, the same operation will preserve it here because the satisfiability of this is just given by the satisfiability. The other direction is this some long code. You can encode testing something as a polymorphism as a CSP, and that's our long code like test. Okay. It's not hard. Yeah. Sometimes, yeah. So in fact, this goes back to what Avi was saying too. So in particular, how do you show something is hard? If the polymorphism is trivial, right, then anything will have more polymorphisms than it. So you can reduce anything to it, in particular, 2 coloring 3 graphs and its NP. Okay, so that's the thing. Yeah, so that thing in the box is called a Galois correspondence because it's called a Galois correspondence. Don't ask me exactly why. I found out once, but I forgot. Because it goes in the reverse direction, right? So, sorry? No, I don't know. Clearly not. But they call it, it's some category theory, such things are called Galois correspondence. So that one is proved using the harder direction of that is proved using some long code thing. But once you have that, this corollary is immediate. Yes, probably, yeah. So one way to do it directly might be to do a long code thing. So you might be able to prove this directly without that box by just doing a long code test. Right? Because we know that once you can test things to be dictators, you can do gadget. You can reduce from label cover or something. Okay, so that's the hardness direction, which is the easy part. Yeah. So. Oh, you have to, yeah, I guess case by case basis, I guess, yeah. But as I said, if it does have by some deep universal algebra results, if it has something, it'll have something of small arity. You can just write a program to check it, for example. Yeah, but that's a good point. I mean, there's no, I mean, you have to do it. Yes. Right. Yes. Yeah, great question. Yeah, so you can also ask, you can go inside P. You can say when is something in NL, when is something in L, and you know these polymorphisms can say things like that. And the other point to answer Avi's question is that in the Boolean case, one thing which is simpler is that Post already gave a complete, this poset of these clones, which is what these polymorphisms are, was already characterized in the 20s or 30s. So the Boolean case is somehow different. We understand the full picture, whereas this such a complete classification of all possible polymorphism objects is not available for higher domains. That's also why it was somehow fundamentally difficult as well. You couldn't just look up in this classification and just say, oh, does this have an algorithm? Does this have an algorithm? Because it already, that classification reduced the infinite to the finite once you have this correspondence. Okay, so now the other direction, and which is what Irith was also curious about, is how do you get algorithms from polymorphisms? Okay, so this is also was alluded. So polymorphisms have this closure property. You can compose polymorphisms with each other, and that will give you another polymorphism. For example, if you have majority 3, I can have a tree of majority 3s, recursive majority. That also will be a polymorphism, just by definition. So using this, you can build more polymorphisms. And in general, by these deep universal algebra, and such a thing is called a clone in universal algebra terminology, things which are closed under composition. By some deep theory, you can show that if these polymorphisms are non-trivial, then it will have highly structured polymorphisms, things like majority or parity, where we can get your hands on it. And then you can exploit them to solve the problem. Okay. In general, this is highly non-trivial. But for the talk, I'm going to have a case study of the very simple case of 2 coloring. Okay, so let me go back to that. So 2 coloring graphs can be thought of in the following way. You have a bunch of equations over 0, 1 of a plus b is 1 mod 2. Or actually over, yeah, you have to solve system like that over 0, 1. Let's think about it that way. That's integer programming. But of course, written this way, in general, this problem is hard. But in this case, we can have many algorithms to solve it. So one thing we could do is, well, it's hard to solve linear program with 0, 1 integer program. So let's solve it over rationals. Okay, we get a linear program. right? So you treat those variables as having to belong in the interval 0, 1. And now you can imagine a way to deduce a true coloring out of this, which is that if something is more than half, you set it to 1, something is less than half, set it to 0. I am sweeping under the rug. What happens if everything is half, which you can assign here? Let's pretend that doesn't happen. Then this algorithm clearly true colors the graph. And then somehow we will see this towards the end of the talk. This is really explained by the majority polymorphism. So the fact that such an algorithm works has nothing to do really with the true coloring predicate. It has everything to do with the fact that majority preserves the relation. Okay, that's how you generalize. You don't really worry about the relations at all. You only worry about the polymorphisms.
Does it mean that you will have some general rounding scheme that
Yes.
polymorphism?
Yes. Yeah. And let's see one more algorithm. True coloring is easy enough. I can give you multiple algorithms. 0 and 1 are integers. So instead of solving them over interval 0, 1, let's solve it over integers. Okay, so you can solve a linear system over integers efficiently. And now there's a natural rounding. Positive things go to 1, negative things go to 0. Every graph, every edge will be properly colored, right? Because 2 positive things can't add to 1, 2 non-positive things can't add to 1. So you'll get a valid coloring. And this is actually explained by another polymorphism called alternating threshold, which I won't define, but basically it's like you put a plus sign on the odd positions, minus sign in the even positions, and see which one has a bigger sum. It's like a signed majority kind of thing. So any template which has this polymorphism, this algorithm will work. Solve over integers and do sign rounding. And the last thing, well, that's a very simple algorithm. You say that, well, just solve the system over F2. It's just linear algebra. So that will work. And in some sense, that's explained by the parity polymorphism, because your space is a linear space because it's closed under a linear operation. So you can solve it with Gaussian elimination. Okay. So those are many cases. And so in fact, true coloring in some sense is the easiest problem. It has this plethora of polymorphisms which lead to plethora of algorithms. But it turns out if you want to generalize, any one of these individual families of polymorphisms itself is enough for an algorithm. Okay, and I kind of, those 3 columns in the last slide were exactly those algorithms. Yeah. 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 Good point. But it's not, I don't know whether there is the map from, I don't know. Yeah, it's a good point, but it can still be a large number, right? And it's finite in advance, yeah. And in fact, that finite number seems to be 2, which is linear programs and linear affine systems. But the problem is they interleave in some very clever ways. And that's why this Bulatov-Zook theorem is so difficult. Yeah. Mm-hmm. No, I'm not sure that, so that's what I said. Some of the instance, really polymorphisms are really defined for the relation. There's no way it will represent for the instance, but not for this, I think. So yeah, in general, yeah. Well, actually, maybe you can, but yeah, but in general, there is no way to exploit that. Because we want to not solve that one instance, right? We want to solve an arbitrary instance. So it's really a relic of the worst case complexity, right? So yes. Right, but then you have structural restrictions on how, yeah, very good. So yeah, this is a worst case perspective where I have no restriction on the constraint tuples where I place them. Indeed, if you place them in some special structures, you can achieve, for example, what Edith is saying, you can encode some other predicate which is easier. You can also, there are also a whole body of work on if the constraint tuples have something called bounded hypertree width, then the problem is solvable. So indeed, there are cases of hard problems which are also easy, because the constraint tuples are restricted in some way. Yes, yeah, for example, if they always come in this 4 pairs together, yeah, then indeed. Yeah, I think that's probably, yeah, we can also discuss offline, but I think it's basically, the point here is that I don't put any restriction on where the constraints can be applied, and then, yeah, then this theory applies. Okay, so for example, one result we proved a few years ago was that if you just have a family of symmetric polymorphisms, namely polymorphisms where ordering the things does not matter. And this was also, I think, your question. In general, polymorphisms need not be like that. And that alternating threshold was not symmetric because you have plus and minus. But if you are symmetric, then a combination of linear and affine equations actually works. And this was discovered in this more general promise CSP thing, which I'll get to. But this actually works for block symmetry. So if you just have pluses and minus, this one actually works. So this algorithm captures all the cases in the previous slide in a unified way. Okay, and I'll come back to this algorithm a bit later. But now I want to talk about this promise CSP detour, which actually led us to that algorithm. Now, I've talked about satisfiability of CSPs, but there are many other variants you can ask. You can ask, find me the best solution if it's not satisfiable, approximate the number, count the number of satisfying assignments. And you can also ask, okay, the CSP is NP hard, so what? Give me the best algorithm. Is it 1.5 to the n or 1.2 to the n? For all these things, there are polymorphic theories, which really give very satisfactory answers. And so for here, I'm going to look at this newest kid in this picture, which is this promise CSP land. Okay, and to introduce that, I want to go back to my favorite problem, which is graph 3 coloring. Right, so it's NP hard to a 3-colorable graph. Okay, but what if I'm allowed to use more colors? So now I'm sort of changing the game a little bit, giving you a little bit more flexibility in solving the problem. For example, you might ask, if I give you twice the many colors, 6 colors, can you 6-color a 3-colorable graph? Okay, and we have the sense that we have a very good understanding of all these problems, but after all these years of research, this is a problem which is open. We don't know if this has polynomial time algorithm or is NP. Sorry? Well, I picked 6 for a reason. It's known that for 5 it's hard. Let me actually put that out here. So for 5 coloring, it is indeed NP hard. And you might ask, what's the best algorithm? The latest record is actually from stock this year, which is, sorry? Not million. Million also, it's okay. So this is the status. 5 coloring is hard. N to the 1/5 colors is easy. Between that, we don't know. But I should say that we have some evidence of hardness. For example, and this was initiated in a beautiful paper of Irith, Elkanan, and Odezregev, who showed that under a variant of the unique games conjecture, any constant is indeed hard. You can't do million and so on. And we weakened this assumption to something called D2-1 conjecture a couple of years ago. But we really believe this should be hard. We just haven't gotten our act together to show hardness. Okay, that's the prevailing thing. But of course, a surprising algorithm would always be nice. So, yeah. Yes. So unique games is in P for satisfiability, but satisfiability, that's, yeah. But no, very good point. Yeah, so we said unique, so this is under, think of this unique games conjecture, which basically says this unique games problem is hard to approximate. But unique games is always easy to decide. It's an easy CSP. Okay, but again, this is this approximation version which makes it hard.
Do you have a conjecture about problem?
Well, I would conjecture any constant is hard. And to show NP hardness. Okay, hats off to Mooley. So, that's the way to find the students you want to take for your PhD there. Yeah, maybe login colors could be enough. Yeah, I don't know. Why not? I don't know. Be an optimist. So, yeah. All right, so that's the status. Okay, where am I going with this promise CSP? So abstracting from coloring, you can say that CSPs are typically hard, but can you solve a relaxed version of the CSP? Does that make it easy? So formally, instead of one predicate, let me have a pair of predicates, P and Q, where P always implies Q. So P is the stronger form of the constraint, 3 coloring versus 6 coloring, let's say. And then you can have 2 instances, phi strict and phi relaxed. So phi strict is just an instance of CSP. But then I can say, can you solve the relaxed variant where I replace all P's with Q's? And that is the PCSP problem. Okay, what is the complexity of this for different pairs P and Q? Okay, and that's the promise CSP. Given that the strict one has a satisfying assignment, the search version would ask for the satisfying assignment for the relaxed. And of course, this strictly generalizes CSPs because you make P equals Q, you get the old thing. But now it's a much, it's a vast generalization of this, which in particular captures problems like approximate graph. Yes, Wei. Yeah, so sick color thing will, yeah, very perceptive. It doesn't quite work because the domains are not the same. So in general, you won't say P implies Q. You will say that there's a homomorphism from P to Q. So or there's a homomorphism, yeah, between. Yeah, that's a special case of homomorphism, which is just a thing. But in general, you could have a more complex homomorphism. Yeah. So if so you can have bigger Q. Yeah, absolutely. Yeah. So yeah, good point. Also, this problem is sort of interesting when both P and Q are hard, but somehow the pair becomes easy, right? Because if P is easy, then you just solve P. If Q is easy, you just solve Q. So the question is that for hard pairs P and Q, when is this pair P comma Q easy? Okay? And let me give you a very nice example of that, which is again this two coloring hypergraphs. So this is of course a hard problem, right? So you can think of this as the Q, CSP Q is hard. But now what if I promise you that there is a two coloring where in every triple exactly one vertex is blue, which coincidentally this example satisfies. But now I say, okay, that's going to be my P, exactly 1 out of 3. Q is going to be at least 1 or 2 out of 3, not all equal. So now is this pair easy? If I give you this promise, can you two color this? Okay. And turns out that it's yes, you can do this, and it's actually a very nice, simple algorithm. It was a very circuitous route for us to find it, but it's very simple in the end. It's a nice homework problem thing. So here is one way to do it. There are other algorithms. Just say x plus y plus z. You know there is a coloring with exactly 1, 1. So put this constraint, x plus y plus z is 1. You can't solve it over 0, 1, of course, because 1 in 3 is NP hard. Solve it over the integers, which you can do. And now do the sign routing. So not all 3 things can be positive. Not all 3 things can be lesser or equal to 0. So you will two color the graph. Okay, so this pair P comma Q is easy. And this is explained by going back a few slides, that affine equation algorithm. The same thing is happening. This alternating threshold is really the key to this working. And somehow this example has played an influential role in the ensuing theory, because it's a sort of this case where this new kind of polymorphism arises, and it has been a useful test bed. Okay, but again, we want to go to a theory here on when you have easy, when you're hard, and we are naturally going to lean on polymorphisms, and it turns out that's the correct thing to do, at least in principle. So how do you define polymorphisms here? Well, you have a pair of predicates. You have an arity M function for any M. When is it a polymorphism for P comma Q? If just, your guess would be the correct one. If you take M tuples in P, apply F component wise. Earlier you said you should get something in P, but now you will just require that it belongs to Q, which is a more relaxed requirement. So you can have polymorphisms when you earlier did not have polymorphisms. Indeed, as I said, this is only interesting when P is hard. So P itself will not have polymorphisms. But if you allow me to map into Q rather than P, I can get polymorphisms. But one big change is, right, the image could be some other thing, so you can compose it with some homo. I just kept it simple here. In general, you just, for the PCSP to make sense, you just need a homomorphism from P to Q, which I'm pretending is inclusion, but doesn't have to be. Okay, so this is, in general, because your output satisfies a weaker predicate, I can't compose this. So this is a bit of a game changer. So you can't just start with one small polymorphism like majority 3, compose it, and make an algorithm out of it. Yeah. Indeed, there are cases where you have small polymorphisms, majority 3, majority 5, even majority up to 1 million, but the problem is NP hard. So you really have to deal with polymorphism families rather than individual polymorphisms. Okay, so this really makes the theory, strictly more complex, and it's still far from clear what the picture is. But they still have some property. I won't go into this definition. There is something, they are closed under this taking minors. So they are these, so this have been called minions now. So now in general, polymorphisms are minions, and you can, again, there is this Galois correspondence like thing. So if your minion is richer, then you are formally easier. So in principle, these polymorphism minions are the correct tool to understand the complexity of PCSPs. It's much more difficult. Okay. So minion is just defined here. You basically can get, for example, majority of 3 is a minion of, is a minor of majority of 5 by just relabeling and identifying variables. So the minion is, yes, so the polymorphisms are minions because if you take one polymorphism and take a minor, you will get another polymorphism. So the polymorphisms are minions, yeah. Minor close family. Yeah. This terminology is not mine, but so these people later call them minions, and the terminology has stuck. So. Okay, so but the nascent theory which is emerging is that if this polymorphism minion is kind of boring, namely all the functions are, let's say, juntas or something, then it's hard. And if they are fairly rich, for example, if they have infinitely many symmetric functions or something like that with very rich symmetry, very much not like a junta, then you get efficient algorithms. Okay, so there are examples of both of these cases, but the general picture is far from clear. We don't even have a conjectured criteria of what the dividing line is. In fact, there may not be a conjectured criteria. There's, maybe there is no dichotomy. Maybe there are problems of intermediate complexity. So all this is possible, but that's where we are now. Okay, and what I want to tell you without too much technical detail is just give you some snippets of what we have some results we have gotten in this flavor, and then we'll wrap it up. So what we have said is that, okay, full PCSP is kind of hopeless, so let's look at some fragments and see if we can understand things. So one of the early things we did was to say, okay, if focus on Boolean already seems difficult enough, and let's focus on the case when P and Q are symmetric predicates. So this 1 in 3, not all equal, these are all symmetric. They don't care about the ordering of variables, just the count of the number of zeros and ones. And there we now have a dichotomy in the PCSP thing. So every Boolean PCSP with symmetric predicates is either polytime or NP hard. And in fact, the picture illustrates the easy cases. Essentially, they're governed by 3 polymorphism blobs. So when you have majority of all odd arities or parity of all odd arities or this alternating threshold, you have algorithms. In the remaining cases, you're hard. Okay, so that's the picture. And yeah, again, this has 2 sides. And again, I won't go into the details, but the algorithm I'm going to it follows from this algorithm I'm going to show you in a bit. This general algorithm, when you have these block symmetric things, that single algorithm actually covers all these cases. And the hardness is a bit more of a case analysis, and the hardness is where you use the predicate symmetry. The algorithm is actually very general. It doesn't care about the predicate symmetry. But in the hardness, you basically say that you must lack these structured polymorphisms. So in using some combinatorial analysis, you then show that the polymorphisms must be junta-like, and then that plugs into standard PCP machinery. Okay, so I won't say anything more about the hardness, but I'll come back to this algorithm in a little bit. Okay, so do I want to talk about robust algorithms? When should I wrap up? 11:35? Okay, should I slow down? Okay. Mm-hmm.
So is there a natural algebraic form of the conjecture here? Like it seems like you kind of sort of prove one for this special case of Boolean here, right? Like there are 3 polymorphisms.
Yeah. No, we don't know. Yeah, not clear. Yeah.
Probability and 6 probability. Do you know that there are no polymorphisms of the form that you?
Well, if we knew a strong enough thing, we would get a hardness. In fact, the way 5 coloring hardness is proved really understands the polymorphisms, which in this case are just 5 colorings of K3 to the n. So by the way, so just to make that point clear, it's a math audience. It's really this, what are polymorphisms for graph coloring? It is just colorings of the powers of the graph, right? So you take K3 to the m and color it with 5 colors, you want to understand how these colorings can look. So for 5, there is some understanding. For 6, there isn't any. And that's actually the problem. So it's a little bit unclear what is the limitation of the structure which is going to lead you to hardness. So I cannot, for 5, it's a bit more complicated. But for 4, I can say this, and the 4 coloring was, of course, known long ago. 4 colorings of K3 to the n essentially look like an arbitrary independent set. And then the rest, if you throw that out, the 4th color, the rest has to be a dictator. 5 coloring is a bit more complex. 6, yeah. 6 you can imagine, right? Because you can sort of interleave 2 dictators in some very complicated way. We don't, but those are great questions. Okay, so robust algorithms, I just want to mention this briefly because again, there's a nice math connection here, which is, so what is a robust algorithm? So let me go back to our familiar cases, long back, Boolean. There are three easy cases: two-sat, Horn-sat, and linear equations. If they're all satisfiable, we have algorithms. But what if the instance is only mostly satisfiable? So 1 minus epsilon of the constraints can be satisfied for some small epsilon positives. Then the behavior of these things diverges quite a bit. So Hastad, in his famous hardness, showed that with a tiny amount of noise, linear equations, there's nothing you can do. You just have to do random guessing. So it becomes extremely hard. And around shortly after, Zwick, in a beautiful paper, showed that for the other two cases, there are robust algorithms. Namely, you can find an assignment which satisfies most of the constraints. So in fact, Zwick got g of epsilon is square root epsilon or something, or cube root epsilon for two-sat. The Horn-sat is worse, exponentially worse, but the point is that g of epsilon goes to 0 as epsilon goes to 0. Okay, and somehow this is a bit, it's also operationally nice because it takes out algorithms like linear equations, which are very sensitive to noise, and somehow only the more combinatorial algorithms survive. And in fact, for CSPs, we have a precise understanding of this. You have a robust algorithm if and only if you are a subset of things called bounded width, which essentially means some sort of local algorithms work, where you just locally check consistency, and that implies global satisfiability. Okay, the algorithm itself is SDP based, semi-definite programming based, but that is the criteria. So we were very curious about what happens in the PCSP case because, and essentially we kind of, I don't want to go into the specific things, but we have a classification again of the symmetric predicates for the robust case. So we understand that out of those three cases, the majority and 80 cases have algorithms. The third case does not have algorithms. Okay, so the three green blobs become two blobs. Okay, and we have a conjecture on what happens more generally, which let me skip here. And the algorithm is based on SDP relaxation. The hardness is quite interesting because it uses Raghavendra's similar result to say that once you get an integrality gap, you can get unique games hardness. Then the whole game becomes finding these integrality gaps. And after some translation, that amounts to certain results in sphere Ramsey theory, which is actually the reason I wanted to mention it here, is that this is nice field where, for example, here is a result you have. So for example, let's just take K is 3. So if I color a large dimensional sphere with two colors, I must find 3 points where the pairwise angles are something less than 120. If they're all 120, I can do the northern hemisphere and southern hemisphere. You won't have a simplex. But if I make the angle slightly less than 120, you must have a monochromatic triple for any number of colors. I stated it for 2 colors. And some, sorry? No, this uses some hypergraph Ramsey theory type thing. So it's not Borsuk-Ulam. Yeah. It's more of a Ramsey flavor. Yeah, so this one is proven, and this covered many of our cases. In some cases, we needed to prove new results of this form. So there's a nice connection to this extremal combinatorics and sphere Ramsey theory. Okay, so I'm finally at the point where I can tell a little bit about this algorithm. So what is this general algorithm if you have symmetric polymorphisms? So the algorithm is this combination of linear programs and affine equations. You run the basic linear program. I'll define what it is in the next slide. If that rejects, definitely you don't have a solution, you go home. You run the affine program. If that also rejects, you go home. If both of them accept, you're saying, oh, you're satisfied. Okay, so it's not exactly this. You have to, between the LP and the affine, there has to be some pruning you need to do, but let's ignore that. And one more important point is that this only solves the decision version. It does not solve the search version, which for promised CSPs are not equivalent. For CSPs, they are. Promised CSPs, they are not. So this is the algorithm. And what is the linear program and so on? Again, I'll illustrate, go back to this two-sat. Okay, rather than two coloring, I'll do two-sat, which is a little more interesting. So essentially, for each variable and each clause, you have a probability distribution. So for each variable, you'll say this is the probability it's 0, this is the probability it's 1, they sum up to 1. For each clause, for example, x1 or x2, there are 3 satisfying assignments. You'll give them some probabilities which sum up to 1, and you will just say that the marginals are consistent. Okay, just the standard thing way you will relax this program. If you haven't seen this before, it might be a bit hard to immediately process, but the point is if these numbers are all 0 or 1, this is exactly the problem. You just relax it to the interval 0, 1. And so if this is not satisfiable, which you can check by a linear program, then definitely you're not satisfied. So that's the first thing. The second thing is exactly the same thing, but instead of saying you are a fraction between 0 and 1, these class and variable things all become integers, which must sum up to. So this is an affine program. And once again, it is, if the instance is satisfiable, it is satisfiable over 0, 1, and so it cannot. So if it's unsatisfiable, which you can check by solving a system of equations over integers, you know you're unsatisfied. And now what we can prove is that if you have infinitely many symmetric polymorphisms, if both of these are satisfiable, you can round them to an honest solution, so it must be satisfied. Okay, but that rounding is not efficient, so that's why it becomes a decision algorithm. Okay, so it's a little bit late in the talk to give the the proof sketch, but maybe I'll just mention one thing. So how do you actually, because also Edith explicitly asked this thing, so how do you actually do this argument? So you write down this thing, so you know that there is solutions for the LP and there is a solution for the integer program. You want to prove that this instance is satisfied. So what you're going to do is that you will use this majority polymorphism, which exists of infinitely many things, so in particular of any high arity you want, to argue the existence of an assignment to satisfy all these clauses. Okay, so what would you do there? So you'll pick you play with these integers capital M and M, so you'll take enough copies. Let's look at one of the clauses. Let's say x1 or x2 must be false. So at least one of the variables must be 0. So what you can do is you can line up lots of copies of the 0, 0, 1, 0, and 0, 1, right? And the number of copies is dictated by the solution in the affine and linear program. And then when you apply the polymorphism, by definition, and you adjust the arity so that you have a polymorphism of that arity, by definition of polymorphism, the output must satisfy the clause. Okay, but of course this is sort of pointless. I've just proved one clause is satisfiable. That's not interesting. But the key point is that the way because of the consistency of the marginals, you can prove that this polymorphism does the same thing on each variable consistently. And that's where the symmetry of the polymorphism is used. It doesn't matter where the zeros and the ones are, it's just their count. So using this, you basically find local satisfying assignments, and they must patch together globally to a satisfying assignment. Okay? And the reason this is not efficient is that in the two-sat case, it's efficient. In general, you don't know how big an arity you need to go to apply these functions. You don't know the complexity of this function. If it's majority, yeah, sure, it's easy. But what if the symmetric polymorphism is some crazy function? Yeah. Mm-hmm.
Why do you only have 0 or 1 values? The integer assignment could have been like.
No. So this is like, see, so this is the clause x1 or x2. There are only 3 satisfying assignments, and each one of them gets a probability distribution or an integer. And that's what those W00 and Z00. It's a usual argument of like lining up solutions. Okay. Right. Yes. Right, but that number could be exponential in n as a number. So because this is a unary problem, yeah. So Avi is saying that these denominators can't be bigger than 2 to the n. So this capital M, you need to clear the denominators, is also 2 to the n. But that's big, right? Because it's now a Boolean function of arity 2 to the n, and that becomes a problem. So really, you would like to have some structured theorem saying that these symmetric polymorphisms can't be very complicated, and then you will get a search algorithm. Okay, I think it's a great direction, but we don't know. Okay, so let me skip this part. So one thing which people got very excited with this algorithm is that they said, well, maybe such an algorithm combining linear programs and affine equations in a streamlined way could solve all tractable cases of CSP. Indeed, it does solve all Boolean cases. So people got excited and they said, well, maybe it doesn't solve it, but unfortunately, it was soon shown that this algorithm itself doesn't work. In fact, it doesn't even work for a simple instance of unique games on domain 5 or something. But people said, okay, maybe there is a Shirali-Adams version of this or some other versions of this which might work. So far, it hasn't borne fruit, but this is a reason PCSPs is given back to CSPs. Even though the dichotomy is established, the algorithm there is very complicated. So it'll be really nice to have a clean algorithm like this, even if the analysis is a bit complicated. All right. So maybe I'll just mention this and then close. So I've been going back to this old loose end. I said there's a linear programming algorithm for true coloring, but of course that's completely bogus, because if I write this linear program, I'll just give half to all the variables that will solve the linear program. So assuming that nothing gets half is completely broken. But you might ask, okay, why don't we solve this linear program over a ring which avoids half? Okay, so maybe you solve it over z root 2. Okay, and why might you hope that such an algorithm might exist? The point is that you can make a convex combination with coefficients in z root 2, namely root 2 minus 1 and 2 minus root 2. So maybe that is prescriptive of an LP algorithm over z root 2, and indeed you can make it work using inspecting standard optimization things. So that's another, and maybe the most complicated true coloring algorithm you might know is to write this linear program, solve it over z root 2, and then your threshold route. Okay. Okay. So thanks to Per Osten and Johan Hastad, literally exactly around 10 years ago, we had this paper on the first PCSP example, and I didn't know that this will lead to sort of much richer theory then, but it has, and that's great. And in particular, a lot of people in the CSP community, I've listed some names here, really got excited and picked this up and pushed the theory in a lot of ways using their algebraic hammers. So that has been very exciting. And a special thanks to the two students with whom I enjoyed this journey, Josh Brackenseek and Sai Sandeep. All right, so time to close. Yeah, what's the big goal of theory of computing is to classify problems as easy and hard, one of the big goals. But you might ask, why is something easy? Why is something hard? And maybe a little bit of science of algorithms. And at least in the land of CSPs and related problems, we have this principle that interesting polymorphisms lead to algorithms, otherwise you get hardness. And one of the frontiers of this in terms of pushing the theory seems to be this promise CSP, which really blends together new methodologies in both algorithms and hardness, but really lots of challenges remain. Concrete questions like sick coloring, three colorable graphs, understanding the structure of these polymorphisms, lots of things. But the nice thing is that these understanding, even if PCSP itself is not your goal, it seems to feed back to CSPs and other areas, so an optimization and so on. So it seems like an interesting thing. Okay? And perhaps the dream is that use CSP as sort of, and these variants as a general enough test bed to get some insight on more broader polynomial time computation. Why do polytime algorithms exist? Which, in some sense, is our main business. All right, so thanks. Mm-hmm. Let me actually put the acknowledgements back for people to see. Yeah. Right, yeah. Yes. Yes. Right. Yeah. So I think now there is a really healthy connection between and appreciation from both ends of approximation and CSP community. And in fact, they have answered some of our questions. This thing I said that you have a robust algorithm if and only if you have bounded width. That's a conjecture me and another student, Yuan Zhao, made, and Bato and Kojik proved it. So there is really just, they even care about some of the questions we ask, learn about semi-definite programs and other things which they did not a priori know, and then use it to blend it with their techniques and produce new science. It's very nice. Yeah. And also this, after the dichotomy, in some sense, it was not, they had solved their biggest problems, right? So where does the field go? But some of this promised CSP has given them a lot of new fodder to push their theories. Oh, bounded with, yeah, so it simply, okay, maybe the most succinct answer I can say is if you write the linear program, few rounds of Sherali-Adams, if you extend this linear program I showed to say 3 rounds of Sherali-Adams, and if that is satisfiable, the instance should be satisfiable. That's what bounded with means. And it turns out, so the result is that you have a robust algorithm if and only if you're bounded with. So if you, for example, take linear equations, no levels of Sherali-Adams or even like sum of squares is going to decide it. And therefore it is not, I mean, not therefore, but it's not, doesn't have a robust algorithm.
Constant negation algorithm could solve the
Satisfiability problem.
and then you get robust algorithm.
For free. Well, not, I mean, then you prove that the SDP, so then what is it? You understand which things such constant round Shirali-Adams can satisfy, and that has some polymorphic structure. You use that polymorphic structure to prove that the semi-definite program will be a robust algorithm. Thank you.